Lesson number 3, let's do some more applications of exponential equations. So if we look at a review of exponential functions, an exponential function is a function of the form y equals ab to the power of x. So the variable is the exponent. When the value of a is greater than 0, when the value of a is greater than 0 and the value of b is greater than 1, I get a growth function. So I get a graph that goes like this. Okay? When the value of b is between 0 and 1, I get a decay function. So the decay function drops like this. Okay? And that's when my value of a is positive. When my value of a is negative, then I've got that reflection that I have to watch out for. So there are a lot of examples of exponential functions in real life. Sometimes they're disguised. The compound interest formula that we did in the last lesson was a disguised form. A is my principal value and b is my 1 plus I. So we can use variations of the exponential function to solve problems involving population growth, the growth of bacteria, radioactive decay, and etc. So if we look at class example number 1. In 2012, a university population of a country was 160,000 students, and it was increasing at an annual rate of 4.5%. Great on video. If the function representing the population is of the form y equals ab to the power of x, what would the value of a and what would the value of b be? So let's start with the value of a.
Is it 160,000?
Yes, it is. So a is my starting point. B represents my factor, whether it's a growth factor or a decay factor. So is this function growing or is it reducing?
Growing.
It's growing, which means in order for it to be a growth function, the value of b has to be greater than 1. Okay? What is it growing by?
4.5%.
4.5% per year. So at the end of the first year, how would I calculate the total population? What would I do?
160,000 times 1.045.
So why the 1 point?
Because if you just did like the 4.5%, it'd just be like how much it grows by would be like the total.
Yeah, and then I would have to still add that to 160,000. So putting the 1 in front of it is basically it's taking 100% plus the extra 4.5. The 100% being the 160. So this 1.045, that becomes my b value. That becomes my growth factor. So it says, write an equation to represent the university population of the country as a function of the number of years since 2012. So my formula would be population P equals 160,000 times 1.05, and we would make this to the power of n, where n is the number of years since 2012. So I could even specify that. N is number of years since 2012. So if I wanted to determine the population in 2015, how many years is that since 2012?
Three.
3 years. So n would be equal to 3. many students do I get?
$182,586.
86 or 87? What am I closer to?
87.
87. So it's worded a little bit differently. It's not when will the population reach this, where I have to always round up or always round down. This one is asking what is the population going to be in 2015. And it's not specifying if we're at the beginning of the year or the end of the year or in the middle of the year. So sometime during that 2015, the population would hit that amount. If the population continues to grow at this rate, determine the number of years it will take for the population to double from its 2012 size. So how would I set up my equation? So doubling means I would have 320,000 students. What would be the next step for solving for n?
Divide by 160,000 over 10. Or
Okay.
160.
So when I divide both sides by 160,000, what do I get over here?
2.
2. And then what would I do?
Turn it into a log.
Okay, so what would my log be?
Well, I did log 2 on the one side and then put n out in front.
And then what did you put on
And
this
then
side?
n log 1.0.
So if I take the log of both sides, the exponent can come out in front. And then to get n by itself, I would divide both sides by
Log 1.0.
And I would get the same thing if I had changed this into a log. I would have had n equals log base 1.045 of 2. And then I'd still have to do my change of base to put it into my calculator. And what do I get for an answer?
15.747.
So how many years would that be?
16.
Okay. If my answer had been 15.23, would it still take 16 years to double? Or could I say it then would take 15?
Wouldn't it still take 16?
It still takes 16 because in 15 years, and I can check this, if I go 1.045 to the power of 15 times 160,000, I don't get 320. So it's somewhere between the 15th and the 16th year that it doubles. Okay. Fish in a lake are decreasing by 5% per year because of overfishing. If the number of fish represented is an exponential function of time, what would be the base, which is the b value of my function? So in this case, do I have a growth factor or do I have a decay factor? It's a decay. So if it's a decay factor, it means that the value of b has to be between 0 and 1. So in the last question, we determined what the total amount would be, and that's how I got the 1.045. That's the total population. If I'm decreasing by 5%, what is my total population remaining?
95%.
95%. So my b value would be 0.95. So then if I write an equation that I can use to represent the number of fish after t years, where n of 0 is the initial population and n of t is the final population. So we're using our exponential equation, ab to the power of x, but what would Y represent in the context of this question? N of T. It's the number after, or it's the final population. And what does A represent?
Initial population.
The initial population. N of 0. We already know that B is 0.95. And X would be T, the number of years. So if I had 2,500 fish in June of 2012, how many would I expect to find in 2017? So N of T would equal, what would N of 0 be?
2,500.
And how many years have passed? 5 years? How many years did you get? Or sorry, how many fish did you get?
1,934.45.
So,
Yeah.
okay. I can't have 0.4 fish. Okay, question D says, how many years would it take for the fish population to reduce to half the number it had in June 2012? So if this is my formula, the initial population is still the 2,500. Do you have a question, Bobby-Ann?
I don't understand why you don't round up for that, because wouldn't it be like you have part of a fish but you can't, so then you have to round up to make it a full fish?
The only time that the rounding becomes the issue is usually when you're dealing with time.
Okay.
If you're dealing with objects, you use regular rounding rules. So population, we use regular rounding rules. It's when we're dealing with time. So how many years does it take? 15 years isn't quite enough, so I have to round up to 16 no matter what.
Okay.
So what's half the number of 2,500?
1,250.
Okay, I give you a couple of minutes and I want you to try to solve this. Okay, so when I go to finish this question off, what's my first step?
Divide both sides by the 2,500.
And then what do I get on the left side?
1/2.
1/2, 0.5. I can write it as a decimal because it's a terminating decimal. And then what would I do at this point?
Turn it into a log.
So when you turned it into a log, what did you do,
I
Rachel?
did log base 0.95 of 0.5 equals t. And then
Okay.
I divided log 0.5 divided by log 0.95.
And how many years do you get?
13.5.
So 13.5 years. Okay. The next question before you've got some practice ones to do has to do with the intensity of a light source. The initial intensity is reduced to another intensity after passing through d meters of fog, and it's using the formula I equals I of 0 times e to the power of 0.12 times d. The thing to realize is e is a constant. It's that constant that is, what's the inverse of e? Look on your calculator. What does it share? What button does it share? The natural log. So this time I wouldn't be taking the log of each side, I'd be doing the natural log. Okay? So it says, at what distance to the nearest hundredth of a meter will the intensity be reduced to 1/4 of its original value? So what's the original value? Do I know what it is? So pick a number. The original value could be 100%. What's 1/4 of 100%? 25. Or I could look at it as, I'm going to leave the initial intensity as I of 0. And the final intensity, I'm going to say, is 1/4 of the initial. So if I work on this side here, my first step would be to divide both sides by 100, which would give me 0.25 or 1/4. And I get the same thing over here. I cross out the initial intensities because they're common on each side, and I'm left with 1/4. Okay? So now on this side here, if I take the natural log of each side, and I can still, the laws for the natural logs are the same as for common logs, so the exponent would come down. What do I know about the natural log of E? It's the same as log 10. Pardon? It equals 1. Okay. Have a seat, CJ. So then if this cancels out because it equals 1, and how do I get D by itself?
Divide by negative 0.12.
Okay. And I want this rounded to the nearest hundredth. Or sorry, yes, 100. What'd you get, Bobby Ann?
11.5524.
So 11.55 meters. Okay. Why is this useful information? Well, what are you driving through? You're driving through fog, right? So if I'm thinking about the distance that my headlights normally travel, and if I relatively know how thick the fog was, 1/4 of my intensity. So if my headlights shine 100 meters in front of me, and I'm traveling through fog that's considered to be 11.55 meters in, thick, now my headlights only work for 25 meters in front of me. Why do I want to know this?
Like, you'll be able to stop in time.
Whether or not I can stop in time. What is my reaction time when I'm traveling through the fog? Do I have enough time to stop safely if I come up on a vehicle or I come up on an animal? Am I traveling safe enough to be on the highway for the vehicles that are approaching, that are coming up to me, and the vehicles that I could be coming up to? This is what an insurance company is going to be looking at. Because if you're involved in an accident during fog, insurance companies investigate things like this because, well, insurance companies are great when they give you the claim. But they don't just say, oh yeah, you got into an accident, here's your money, there you go. They investigate whose fault was the accident. And if you're seen as traveling too fast, given the conditions, they can refuse to pay for the claim. And then you're paying out of pocket. Okay, so the questions I want you to practice are 1, 3, and 5. and I'll give you probably about 5 or 7 minutes, and then I'd like to work on the next part.
So we could try to support them.
Okay, looking at half-life, doubling time, etc. Radioactive substances decay by changing into a non-radioactive substance. The amount of radioactive substance present at any time can be given as an exponential function of time. And then after a certain time, interval time h, called the half-life, only half of the original amount will remain as being radioactive. For some base, b, we can write the exponential function as a equals a of 0 times b to the power of t, where a is the initial amount present at time 0, a is the amount left over at the end, and then you have your base, and then to the power of t. So radioactive decay is what we use when we're doing carbon dating. So when they find those dinosaur bones that they keep digging up in this area for the museum in Wembley, when they're doing tests to find out what era the dinosaurs came from, that's what they're doing, is they're looking at the amount of the radioactive substance that's left in the bone, or not the radioactive, they're looking at the amount of carbon left in the bone, and they're using the idea of half-life of the carbon to determine how old the bone is. So in this case, the B, or my base, is 1/2. Okay. Not here. Were you learning the math? So what I end up with is I end up with this function where I have my base as being 1/2, but this exponent here becomes a t over h. And the t and the h refers to the time that has elapsed and the half-life of the subject. So when the time is equal to the half-life, half the substance remains. So I get that the final amount is equal to half the initial amount. So that's what I substitute into this formula. So then when I put the two formulas together, that's where I get the t over h that comes in. What you need to remember from this is what is the t and what is the h. T is the time that is elapsed. H is the half-life of the material, because scientists have determined how long it takes for different materials to break down into half the amount that they started off with. We can go the other way and we can determine doubling time. So in doubling time, my base is now a 2, but then what I get is this t over d, time over the doubling time. Okay? So the next page actually summarizes it all and gives this to us as a single formula, which again is still derived from my exponential formula. So in my exponential formula, y now becomes the final amount at time t. A is my initial amount at time 0. B is my base. Now if we're talking half-life, my base is 1/2. Doubling time would be 2. What would tripling time be? 3. And so on. And then I've got this t over p. That's my exponent. In this t over p, t is the time that is elapsed, and p is the period of either the doubling or the tripling or the half-life, this constant amount. Oops. So we're going to put this into using on a couple of questions of where this becomes important or where this actually gets used. So we have a patient that is feeling ill, so they go in and they get a throat swab. So bacteria is taken, sample from their throat, and the sample contained 387 cells. 24 hours later, the sample was recounted and was found to contain 8,012 cells. So the question is, what is the doubling period of the bacteria to the nearest tenth of an hour? So if we use our formula, the amount at the end equals the amount at the beginning times this constant, which is going to be 2 because of the word doubling, and then I have t over p, time over the period. Do I know how many cells I had at the end of my time?
8,012.
Do I know how many I
Sorry to
had?
interrupt. With the senior girls and boys volleyball team, please make your way to the front to help with the A&W sale. Thank you.
How many do I have at the end? Or sorry, at the beginning?
386.
Okay. How much time has elapsed in the course of my experiment? 24 hours. And P is that period. It's the doubling time that it takes for the bacteria to double. That's what I'm trying to solve. Okay? I'm going to stop it there. It's going to take me longer than a minute to do this. So we've got the formula initially set up. 8,012 is the number of cells that we had after the 24-hour period, with 387 cells, what we started off with. And then the time that elapsed was 24 hours, and it's the period for the doubling time that I'm trying to find out. So what would be the next step in solving this question?
Divide by 387.
Okay, so if I divide both sides by 387, what do I get? Do I get a number that works out nicely?
No.
No. So we're just going to leave it written as a fraction form. So now what would I do? How do I pull this exponent down? I use logs. Now, because my exponent is, I'm going to say, a little bit more complex, being the 24 over p, it's probably easiest if we actually write it and take the log of each side. So I get 24 over p times log 2. So if I have p as a denominator, how do I bring it up to make it a numerator? So instead of dividing by p, multiply by p. So I'd multiply both sides by p. So I'd have p times this log 8,012 over 387 would equal 24 times log 2. And then to get p by itself, I would divide by that log 8,012 over 387. And tell me what you get for an answer. What'd you get, Rachel?
5.4897.
So to the nearest tenth would be how many hours?
5.5.
So it takes 5.5 hours for the doubling time. What are some of the purposes behind knowing the doubling time of the bacteria? What does knowing its doubling time allow me to do? Yes, I know we're doing biology in math class. And we're listening to kids laugh down the hallway. Why do I want to know how fast this bacteria doubles?
So you can know how much medicine you need to kill it.
So that I know the medication to kill it, or to at least reduce the numbers, and can also tell me what kind of bacteria I have. Because different bacteria is going to multiply differently. So knowing those two things allows me to make sure that the medication that I've probably already prescribed, because most of the time the doctor gives you the prescription, before they actually have the test results back. But if something comes back differently, then they know whether or not the medication was going to work properly. Also the dosage. So that's why when you get your medication and it gives you the dosages, you have to follow it, because what they've determined is if I take it at this time, it kills this many bacteria. And then the bacteria grow, and then I take it again and it kills off that many more. So if I don't take the medication on those cycles, it allows the growth to come up, and then when I'm done the medication, I'm not actually in the safe zone where my body can combat the bacterial infection on its own. That's what you're trying to do with the antibiotics, is get it so that your body can fight the infection. Okay, so the next example looks at Chernobyl. Before you guys were born now, I remember this somewhat clearly. So Chernobyl, which is a city or a location in Russia, they had a nuclear accident, which is why people really don't like nuclear power. So when this accident happened, it contaminated the atmosphere with radioactive iodine-131, which is extremely carcinogenic. So it can cause cancer cells to multiply and to produce much faster than in normal circumstances. If the half-life of the radioactive iodine is 8.1 days, determine the number of days it took for the level of radiation to reduce to 2% of the original level. So if I start off with my main formula, which looks like this, and then if I list off my variables along the side, what are some values that I know? Is T 8.1 or is P 8.1?
P.
P is. How do I know that it's P?
Because that's the half-life.
Because it tells me it's half-life. Okay, which means that C would have to be equal to 1/2, because C is that constant. So doubling, tripling, half-life. Okay? T is what I'm trying to determine.
Couldn't you just make like the initial amount 100 and then 2% of 100's due?
So if I just assume that at the moment of the accident, 100% of the iodine got released into the air, and now I'm looking for 2%. So then I'm not worried about how many milligrams or micrograms or whatever the unit would be. I'm worried about the percentages. So I get 2 equals 100 times 1/2 to the power of T over 8.1. So take a couple of minutes and see if you can solve that equation.
I might wrong, because
Okay, so what would be my first step?
Divide by 100 on.
Okay, and when I divide by 100, I get a nice decimal, so let's use it. Okay, so now I'm at this point. I need to pull the exponent down. So what allows me to pull the exponent down?
Make it a log.
Taking a log. And because I'm looking at a more complex exponent, it is easier to take the log of each side rather than writing it in log base form. Okay? Now because T is a numerator, I need to get rid of the other stuff. Okay? So if I look at this 8.1, the operation that is happening with the 8.1 is what operation?
Dividing it.
Dividing it. So how do I get rid of it?
Multiplying.
So 8.1 times log 0.02 equals T times log 1/2. And then to get T by itself, what would I do?
Divide by log.
Divide by log 1/2. So t is going to equal 8.1 times log 200 divided by log 1/2.
Just put in 81. Oh my god, I put in 81 too.
Aha.
That's why I got it.
So when you put 8.1, what do you
Oh,
get?
I got it. I don't know what I did before.
45.71.
That's right.
So how many days?
46.
46 days. Will the level of radiation ever equal 0?
No.
Remember, exponential equations get to the axis but never actually cross the axis. So the value will never equal 0, which means that after a nuclear accident of this level, the level never actually gets to nothing. And that's the part that is concerning, is the fact that there's still an amount of it that is left in the atmosphere or in the air. And even though it only took 46 days to get down to this level, in those 46 days there was still that exposure. And that's what can be the safety factor behind nuclear power. It's a clean burning, it's a better power than a lot of the coal and the wood burning and the oil that we take out of the ground. But when there's an accident, it's not good. Okay? We'll do the next question tomorrow. Example number 6 when dealing with these exponential equations. So we've got a radioactive isotope. It has a half-life of 7 years. If we use the formula A equals A of 0 times C to the power of T over P, with C, the constant, being 1/2, and even if it didn't tell me, the fact that it says half-life, I should be able to know what that C value is. Determine how much of the isotope must initially be present to decay to 60 grams in 14 years. So if I use this formula, 60 is my final amount, and A of 0 is my initial amount. I've got 1/2, and what is T? How much time has elapsed in this question?
14 years.
14 years. And what is the period of my half-life? 7 years. But 14 over 7. What is 14 over 7? 2. So 60 equals A of 0 times 1/2 squared. What's 1/2 squared?
1/4.
Yep. And how do I get rid of 1/4? Multiply by 4 on both sides. And what is 60 times 4? 60 times 4?
240.
240. Is that what you said? Oh, sorry. So 240 grams would be what I initially had at the beginning. Okay? There is another way that I can actually figure this out. In year 14, I have 60 grams. And it decays by half each time. So that means in year 7, I would have had to have 120. And then in year 0, my 240. It works out nicely because 14 is a multiple of that period of time. If it's not a multiple of the period of time, you're not going to be able to draw it out like that. Now suppose I wanted to write this formula. For some reason the division button is broken, so I can only multiply. So I can't even write this as 1/2. How can I change this formula to use a 2? So instead of having 1/2 to the power of 2, what would I have? 2 to the power of what?
1/2.
Not 1/2. So when I have a reciprocal bit, -2, good. And then question C says how this solution could be found without using a formula. This is how it can be found without using the formula. This is how we did it up here. And like I said, that only works when it is a multiple. If it's not a multiple, you're not going to be able to use that process. So the questions that I would like you to work on